Hello everyone, welcome to my presentation. I am Serkan Hasanoglu. I am a PhD student in earthquake engineering at IUSS Pavia, and my PhD advisor is Professor Gerard O'Reilly. In this presentation, I'm gonna talk about the recent work that I have been doing on for the integration of specific data for reinforced concrete frame type buildings into the recently developed simulated design platform. Let me start by introducing the outline that I will be following through the presentation. First, I will talk about the seismicity and design costs in Turkey. And after that, I am gonna give you some general information about the reinforced concrete building stock of the country. And then I will show you some previous studies done on the seismic fragility of Turkish RC frame type buildings. And after that, I'm gonna start talking about sim design framework by giving additional information about the data that I integrated into the framework for Turkish RC frame design classes. And finally, I'm gonna show you some example applications that I used simulated building models from Turkish design classes as well. Now let's start with the seismicity of the country. Here is located in one of the most seismically active regions in the world, where the seismic activity occurs mainly due to the interaction between African, Arabian, and Eurasian plates. The northward motion of the African and Arabian plates causes some compressional forces as they collide with Eurasian plate, and this interaction causes the westward motion of Anatolian block throughout the North Anatolian fault and East Anatolian fault. And besides this tectonic setting, there is also an important tectonic setting in the region, which is called Aegean Graben system, which further increases the seismicity of the country. And due to this high seismicity, the country has experienced 21 earthquakes with moment of 7 or greater since 1900. And among the most devastating were the 1939 Erzincan earthquake with moment magnitude of 7.8, which caused to more than 32,000 fatalities and about 100,000 injuries. And subsequently, the 1999 Izmit Kocaeli earthquake with moment magnitude of 7.6, which also occurred very big catastrophic effects. And recently, the 2023 Kahramanmaraş earthquakes caused to more than 50,000 fatalities and about 100,000 injuries. Now, after this seismicity and the catastrophic effects the country had observed so far, and now I want to give some brief information about the design costs in the country from past to current time. The first building code in the country was introduced in 1940, and it was based on the Italian building code of that time. And after this code, subsequent revisions was made, but none of these seismic design codes included details for the design of reinforced concrete frame type buildings. And after that, in 1968, the first seismic design code, which includes specific details for RC buildings, was released, but it included only very minor details for the design procedures. And in 1969, the first version of TS500 code, which is actually the reinforced concrete design code in the country, was published. And in 1975, the first modern or comprehensive seismic design code was released, which was including some details for ductility, requirements at element and also structural level. And subsequently, in 1975 and 1984, some revisions was made for the TS500. What the most critical change was happened in 1984 version by adding the ultimate strength method as an option to allowable stress method. Until that time, allowable stress method was the only option that was used in the typical RC design procedure. And in 1998, a new seismic design code was released. It was included some modern design concepts such as capacity design rules, strength reduction factors, some advanced analysis options such as multi-superposition, nonlinear time history analysis, and so on and so forth. And it was also including some ductility levels to be followed in building design as high and moderate ductility. And in 2000, the last version of TS500 was released by making the use of ultimate strength method mandatory. And in 2007, a new seismic design code was released, but it included very minor changes on the design of RC buildings. But it included new chapters for the assessment and retrofitting of existing buildings. And finally, in 2018, the last seismic design code of the country was released. It included significant advancements such as modern spectrum-based seismic hazard map, and also it adopted performance-based design approach for the first time. And it also accounted for the crack section stiffness modifiers in the design procedures of the country for the first time as well. And not only design regulations, but considered design forces changed over time. In the figure on the right, you'll see the variation of lateral load coefficients, which is defined as the lateral earthquake load to the ratio between the lateral earthquake load to total structural weight. And you'll see the variation of this parameter from the 1949 seismic design code to the last seismic design code of the country. And now in this slide, I summarized some important information for the RC building stock of the country. Mainly the mid-rise reinforced concrete frame type buildings constitute the dominant structural typology. And most of these buildings were constructed after 1980. And also the seismic design codes, which were released after 1975, were at good enough level, but many buildings constructed before 2000 exhibited significant structural deficiencies in the past catastrophic events. But the main reason behind these structural deficiencies was the non-engineered and unauthorized constructions, poor construction quality, and lack of effective inspection system. And in 1999, after the Kocaeli earthquake, a significant turning point occurred in the construction practice, and several changes happened. And the first one was, of course, the seismic design codes began to actively implemented in design procedures. Ready-mix concrete production was spread throughout the country, and its use became mandatory. Also, the use of ripped reinforcing steels became mandatory, and a construction inspection system was introduced in 2001. And because of these changes, the quality of the construction was improved dramatically. When we look at the fragility curves generated for the Turkish RC frame type buildings, we can find several studies among these. The Akkar et al. 2005, Erberik 2008, Kırçıl and Polat 2006 studied for the buildings constructed before 2000. And Hancılar et al. 2020 studied the buildings constructed after 2000. And all of these studies use different modeling and analysis methods, and also utilize different intensity measure types. Now I will start talking about sim design framework. But before starting, I just want to give the main motivation behind. As you all know, the existing vulnerability models are difficult to use for large-scale assessments because of several reasons. Because they are mainly developed using different numerical modeling and assessment approaches, they generally lack clarity regarding design rules. They were developed for different intensity measure types, different damage measures, different damage state definitions, thresholds, etc. And they use broad building class definitions. And in most of the cases, they rely on limited archetype structures, which causes to failing to capture building-to-building variability. And because of, especially because of the last point, recently, a simulated design framework was developed as a part of Built Environment Data Initiative, and its source code is available on GitHub. Actually, this code was adopted in European Seismic Risk Model 2020. If you just check the fragility curves utilized for reinforced concrete frame type buildings in this project, all these fragility curves were developed using this code. The framework requires several inputs. First of all, structural system. The original code was prepared only for reinforced concrete frame type buildings, but other structural systems are aimed to be integrated in the future. And the original code prepared for the RC frame type buildings were generated for European general RC frame buildings, and there four distinct design classes were developed for this purpose for different levels of seismic design considerations, from no seismic design to modern capacity design which includes capacity design requirements. But all of the countries may have different design procedures, design rules. Even if two countries follow same design rules, they may have some differences in their structural properties, maybe about their geometries, material preferences, etc. For this purpose, it is necessary to integrate some country-specific design classes into the framework. For this purpose, I developed 5 different design classes representing the Turkish reinforced concrete frame building typologies. And the abbreviation was constituted by simply connecting the terms. The first term represents the name of the country. The second term represents the construction period. And lastly, the last term is the level of ductility to be followed in design. And this is the case only for the buildings constructed after 2000, as given in the design codes of the country. By giving the information of structural system and design classes, the other required parameter is the beta coefficient, and also number of stories, portfolio size. When we give these required parameters to the framework, it starts doing the random sampling process to calculate several building attributes. And for this purpose, different probability distributions are required to calculate all the parameters that you see here in bold. And the required probability distributions are generally available in the literature. For Turkish building classes, I utilize the studies you are seeing here on the left with the main reference of Bal et al. 2008. And I integrated the required probability data into these JSON files prepared for the Turkish design classes. And after finishing the sampling phase, all these attributes are stored in a Python class called building class information model. And iterative simulated design procedure is initiated. In this process is actually the main work, the main part that I worked on, because it was necessary to understand and code all of the Turkish design codes, seismic design codes, as well as the RC design codes. And now I will show you the design algorithm that the framework follows. It mainly starts by defining the preliminary section dimensions according to the minimum design requirements of each seismic design code. And then it runs some linear elastic analysis for all load cases, which are defined according to the load combinations defined in design codes. After that, the section dimensions are controlled. If they are adequate, section reinforcements are started to be calculated. And after this process, the design is again checked. Some ductility requirements are checked in this process, for example. And if the design is adequate in this phase, also the design is finished with solution. And for the design of section reinforcements, first the longitudinal and transverse reinforcements of beams are calculated, and then longitudinal and transverse reinforcements for columns are calculated. And in all of these steps, I integrated the required data for Turkish design codes. And if of course, if the capacity designs are followed, additional design forces were added to design forces to consider the strong column weak beam principle. And differently from the European design classes, for the design of longitudinal reinforcements, I developed a longitudinal reinforcement area calculator for biaxially loaded reinforced concrete rectangular column sections, and prepare some design charts for columns for different steel types and for varying axial load ratios. And after calculating these reinforcements, and the code checks the section dimensions and requirements. If it is okay, the code gives a solution model, and it gives a model. But if it is not the case, the section dimensions may be increased, but it is not. If it is not possible, beam types, material types, and column types can be changed, and all the process can repeat it afterwards. And after getting the design attributes, a quality-based design modification process is started. In this process, parameters like concrete strength, steel strength, concrete cover, stirrup spacings are modified to consider the variability in the rail construction. Basically, for the parameters you see here on top, a median value of 1 and standard deviation value for different levels of quality are given, and some quality factors are sampled and multiplied with design attributes. But this process is applicable only for only for code-conformed buildings, but this is not the case for the buildings constructed before 2000 in Turkey. For this purpose, I also tried to calibrate the quality factor to match the design attributes with the design, probability distributions in the literature for these design attributes. And after this step, design attributes are stored in BDIM class and numerical model generation is initiated. In this process, concentrated plasticity approach is followed by using state-of-the-art methods in the literature. I will not go into detail in this part because they were already presented in the previous ROS seminar. Now I will give you some example application results. In the first example application, I generated 100 different building models, 100 different four-story building models for each design class defined here in the table. And the beta values were calculated assuming the buildings are located in a stiff sandy soil site in Zeytinburnu district of Istanbul, and assuming that building's story height is 12 meters and calculated the approximate fundamental period of vibration by using the empirical equation in the 2018 design code. And also I included EU CDL and EU CDH design classes into the analysis because they were utilized to represent the RC frame buildings in the European seismic risk model study. And also the moderate ductility cases was not allowed in this study area, but I included them to just make a comparison. And all the other parameters were defined by engineering judgment by looking at the seismic design codes and also the probability distributions in the literature for material properties actually. In this figure, you basically see this sampled attributes, sample taxonomy attributes, and geometry variables. Actually, you see the variability exists in the simulated models, which inherently shows the variability of the simulated building models. And after generating the building models, I applied nonlinear static pushover analysis on each building model for X and Y directions. For example, if you check the figure on the left, you can easily see the effect of enhancements in seismic design procedures and codes. Because the buildings constructed after 2000, I mean, these curves on the top are having more strength and ductility levels than compared to buildings constructed before 2000. And you see some differences between EU-CDH design class, which is the dashed blue curve here. These are the median curves. Actually, I forgot to say that. These are the median shovel curves. And you see there are some differences between the strength level and also ductility level. But most importantly, there is a difference between the strength values of EU CDL design class and also the TR 7599 design class, which simulates the buildings constructed before 2000 in Turkey. And by using these pushover curves, I calculated capacity curves, then set the equivalent single degree of freedom models, applied nonlinear time history analysis, and eventually I calibrated the fragility models and compared them with the fragility models from the literature. And as you see here, for example, when we compare the black, yellow, and red curves, they are close to each other. There is some difference, and it is mainly due to the reason that we didn't include the infill walls into models, because the option of infill walls in sim design was recently added to the framework. So the difference may be due to that reason, or maybe the literature models may be wrong in some level. But another important thing here is the amount of dispersion we get. They are higher than the dispersion values in the literature models. And after that, by using these fragility curves, I conducted a probabilistic seismic hazard analysis in the study region and combined the fragility curves and used damage to loss ratio models in the literature, Martins and Silva 2021, and get these loss-related outputs. As you see here, for example, expected annual loss ratio for the buildings constructed before 2000 are extremely high, and compared to the buildings constructed 2000 as expected. I also compared the mean annual frequency of collapse values and added the suggested threshold value given by ASCE. As you see here, the threshold is far below than the value calculated for the TR0018 DCH class. The reasons may be due to the reason that we didn't include infill walls. But even if we included them, it is certain that we will not reach to that suggested limit. And in the second application, I investigated the effect of different modeling and assessment approaches. Basically, I generated 100 different 3D multi-degree of freedom models, then converted them to equivalent single degree of freedom alternatives, and also I generated stick type reduced order multi-degree of freedom models, which the recent version of vulnerability model toolkit of GEM is based on. Then I conducted different analysis options such as multiple stripe analysis, cloud analysis on all these all these modeling options, and compared the effect and investigated the effect of all these assumptions. And as you see here, for example, for the collapse fragility case for demi state 4, there is a difference between the fragility, the probability of exceedance of collapse values. When we use the multiple stripe analysis, for example, they are giving higher probabilities than the values from the cloud analysis. But when we change the intensity measure, for example, from spectral acceleration to average spectral acceleration, the median intensity values gets closer. So this kind of information is valuable, especially for our regional studies, to decide on which modeling strategy is better, which analysis type we should follow. And also, additionally, I utilized these fragility curves, and by also including some hazard curve from the study area, I compared these effects on a loss metric, average annual loss ratio. As you see here, when we use the single degree of freedom models, the expected loss ratios are considerably higher than the other method and other modeling and analysis options. But it is interesting that the stick models are pretty close to 3D alternatives. So probably they are better alternative than the stock models case. And so all these informations gives us some important information for the decisions that we made for these modeling and assessment approaches that we do in regional seismic analysis. And this is the paper we published for the work we did for the Turkish RC frame type buildings. And this is the end of my presentation. Thank you very much. If you have any questions, I would be happy to answer.
Thanks, Serkan. Do you have any questions or comments?
Yes, please.
Yeah, thanks a lot, Serkan. I just had a couple of questions.
Yeah.
You are, let's say, aware of the recent developments in the simulated design framework. I just wanted to ask, since you presented fragility, it means you done nonlinear chemistry analysis.
Yeah.
I wanted to see if it has been integrated as an option, or is it still on the nonlinear stack for sure? So can you do nonlinear chemistry analysis?
Yeah, I can do nonlinear time stories, but the framework just gives us some building models, and then I separately conduct nonlinear time story analysis with a different code I prepare.
Okay, so you brought in a framework to combine it with this.
Yeah, exactly. Yeah.
And another just comment. Yeah, very interesting comparisons when you see the different modeling approaches and seeing how the stick model is able to replicate more or less what the simulated design framework.
Yeah.
I was just wondering from a use case application, were you using the stick models the way they are, or did you do some calibrations on the hysteresis?
No, I didn't. I just used the same parameters that the vulnerability model toolkit uses. Actually, I haven't changed anything. Also for SDOF models, I use the same degradation parameters in the static models defined. Thank you.
Questions, guys? That's awesome. Yeah, thank you, Serkan, for the presentation. It's a very interesting part. Yeah. To ask you about the quality factor.
Yes.
You said that you estimated that from integer.
Not quantified. Probability distribution.
Yeah, probability.
Yeah.
Let's go check. You estimated those from integer values.
Yeah, actually the red curves are from literature, and the dashed blue curves are the sample design attributes I get from the simulated design framework. Basically, I tried to calibrate these blue curves to match with the literature curves by calibrating the quality factors. Because otherwise it doesn't make sense to use the building models, because for example, for concrete strength, if we just use some empirical equations for the expected values of concrete strength, for example, C14 concrete, it is around 18 megapascal. But when we see the concrete strength values in the country, they are in most of the cases for C14 type concrete, it is lower than 10 megapascal. So I should also needed to decrease the medium values of the quality factor. That was the reason behind the calibration.
And do you know, like the values you found in literature are based on that real?
Yeah, they are based on real data that people just gathered from in Turkey, of course.
Because I was thinking, like, if you wanted to apply, let's say, this framework on a different code tree, like, it might be hard maybe for that particular.
Yeah, of course.
But you found them.
Yeah, from the literature, and all of these studies were the studies investigating the Turkish buildings.
Very well. I have just one question on the PhD, and I see the showing curves. in 2018 we changed the code. And when I see the medium short curves, if I'm not seeing wrong, what is the difference between 2008, post 2018 and 2018, 2000 to 2008?
Yeah.
And I think the reason will be because the betas are almost same.
Yeah.
And but then are you using different quality factors or
Quality factors are also very similar.
Okay. So yeah,
So-
I guess I give my answer with me instead. So you basically consider that post 2000 buildings have a similar beta and similar.
Yeah, actually the values are all here. For example, for post 18, these are the quality factors. 80% of the buildings having the high quality for post 18, and for the other design class it is 60%, but it is not that big difference, I can say.
It's interesting to see that
Yeah,
change building code and the end result is not changing.
yeah, maybe the economical effects might be different. We don't know. Investigate them as well.
This point, in my opinion, the main difference happened in 2000 after 2018 was not the way to do this mid-rise, low-rise.
Yeah, it's also an issue. Yeah.
Because if you start checking the design rules, they're not that different than before, actually, for those type of buildings. That's the main reason. Also, the hazards in Istanbul did not change that much, but maybe in some places it changed a lot, so that can be the difference. Because this is only for Istanbul.
Yeah. Yeah, there are some changes even for the reinforced concrete frame type buildings, but they were not that different. So the analysis results are very similar. This is the result. Thank you.
Yeah, I was going to ask all of this in both response. Because it seemed like, as you said, change the design, but change back into they had there, right? But I know that the beta values were similar in each case, so that means you have essentially the same ladder of design strength if you go back to the previous table. Yeah, so you're seeing the same thing. Okay, the quality got a little bit better. You hope that you're getting a little bit better quality. But was there any significant change in design rules? Like you could design it in the same ladder road coefficient, but not have capacity to design. For example, like that's a fundamental rule that we have everywhere now. But was there any big change in the design rules between 2018 and post 2000?
Yeah. Yeah, the level of ductility, if I not wrong, were in the last design code it is 8. In the previous code, I think it was 7. But just a little difference there. And the beta value is the same, so the strength values are similar for that reason. Maybe just because of the difference in R factor, there is some increasing in the ductility level actually.
And did you change anything in the model between those?
No, they are same. Yeah.
Here we assume no shear failure at all.